Mr. Kyle, we sure have learned a lot about water in the last few weeks, but how does water get to our houses?
Well, that's the job of someone called a hydraulic engineer, and they're scientists that understand how water works and fluid dynamics and how to get water to and from your houses.
Wow, cool. Let's learn some more about that.
Okay, go.
We are so lucky to have clean water that comes directly to our house and comes out of pipes in our walls. A couple hundred years ago, if you wanted water, you had to get your buckets and go down to the river or down to the lake or have a well in your yard, or maybe the well was in town and you had to carry the water that you needed up to your home.
Today, thanks to indoor plumbing, we don't have to go get water. We get water brought to us. Usually, water starts at a dam or a water treatment plant and is then moved to a water tower or some kind of container that's usually kept very high up. And that's so water is able to flow down into our neighborhoods and cities and fill up the pipes in the walls in our houses to bring water right to where we want it. And that water gets to the houses because of that weight of the column of water. You guys remember when we had the jars of siphons, and every time the jars were uneven, the water levels wanted to become even? And this is exactly how this works. This is like the top of the water level, and it is trying to even out through all the pipes in the houses.
Hydraulic engineers spend a lot of time with this formula and the three concepts that make it up: flow, pressure, and resistance. Flow is just a fancy word for how much water, the amount of water. Pressure is the force exerted by water or on water. And resistance is anything that slows water down. Okay, so flow is pretty simple. If I pour this jug of water, water flows out. The opening is going to dictate how much water flows. So I've got this nice big opening, and when I pour, I get lots of flow. Whereas with this smaller bottle, I have a little tiny opening, and it gives me a little tiny bit of flow. So, the pipes in your neighborhood are found underneath the streets in your neighborhood going to your house, and they are big pipes. Why? Because they want to provide lots of flow. It has to provide plenty of water for every house in the neighborhood. Now, when the pipe breaks off to go to each house, it's a much smaller pipe because each house does not require as much flow as the whole neighborhood. All right, pressure is how much squeeze is put on the water, or how much force is put on the water, and thus how forceful the water becomes because of it. Now, if I just squeeze this bottle a little, I get a little bit of flow. But if I squeeze this bottle really hard, I get a lot of flow. Increasing pressure is going to increase the flow. Thanks, Mr. Kyle. Resistance is stuff that slows water down. So for instance, if I don't have a cap of any kind on this bottle, there's very little resistance to the flow of the water. So low resistance, high flow. If I add resistance like this cap with a little tiny hole in it, I increase the resistance and decrease the flow. Now, in order to get more flow, I'm going to have to increase what? pressure. Yeah, because this isn't much flow, but if I add pressure, I can add to the flow. Sorry again, Mr. Kyle. Sorry, Mr. Kyle. It's really hard to play with not water and not splash the people around you.
I know.
You know what? I
What?
think the best way to discuss pressure, flow, and resistance is to go play on the water table.
Oh, we have one of those.
Yeah!
Let's go.
To the water table.
All right, now it's time for our water table experiment about pressure, flow, and resistance. I have a pipe that's 1 inch in diameter. This one's gonna go over here. And then I have a pipe that is 3/4 inch in diameter. And over here is a pipe that is 1/2 inch in diameter. And before we start, I gotta plug off all of these so that all of our water comes out of these 3 pipes. Now, our question is, which one of these pipes is going to have the most flow? The 1 inch, the 3/4 inch, or the 1/2 inch?
I noticed they're all the same height this time.
They are all the same height. Last time we talked about different heights of columns of water, but we're not measuring that today, so we're keeping our variables in check by making sure they're all exactly 12 inches tall. So we have to figure out which one is going to have the most flow, which one is going to have the most pressure, and which one is going to have the most resistance. Go ahead and take a minute, think about it while I turn on the water table.
Woo!
Alright, so here's what's happening. The 1 inch pipe has the most amount of water coming out of it, but you can see the column is not as high because although it has the highest flow, it has very low pressure. And the 1/2 inch pipe has the highest pressure because it is the smallest one. And that's why our column of water is coming out the tallest.
But Mr. Kyle, I don't see what that has to do with resistance.
Well, that's simple. If you add resistance, you lower the flow, but you increase the pressure!
I probably deserve that. Well, Mr. Kyle, the relationship between flow, pressure, and resistance is kind of interesting because it lets us talk about the direct and indirect relationship between these 3 concepts. For 4th through 6th graders who have worked with fractions, you will see that like anything that's a whole number, you can just assume that it's over 1. And then anything above this line across the equation is going to have a direct relationship, which means when pressure goes down, flow goes down. When pressure goes up, flow goes up. In contrast, anything below this line is going to have an indirect relationship with flow. For resistance, when resistance goes up, flow goes down. Remember, resistance is blocking that flow. And when resistance goes down, flow goes up. You see how that works?
Wow, Miss Reinfelder, playing with water can be a lot of fun and scientific.
Yeah, absolutely. So kids, at home this week, I would like you to try out one experiment. And you can do this with your hose, or you can do it with the bathtub. What I want you to do is get a bucket and a timer. And if you are in the bathroom, I want you to stick the bucket under the tub faucet, turn it on full, and see how long it takes to fill up the bucket. Then empty the bucket and switch to the shower head. And if you look at the shower head, you'll notice that it's got lots of little tiny holes. That's adding what? Resistance.
Oh, that's
Yeah, it's adding resistance. And so what do you think that's gonna do to your time to fill up a bucket? Try it out. You can do it with a hose too. If you have a spray nozzle on the hose, you can do it. Take the spray nozzle off, fill a bucket, time how long it takes, and then put the spray nozzle on the hose and fill a bucket and see how long it takes. Give me the results in your comments.
Let's go play more with the water table.
Yes!
Bye!
Bye!